Welcome to the third lecture of our conference on science and personal action, human and divine. To give you a little bit of background as to why I was so grateful to have our speaker, I should explain that before I went to seminary, I bought a book actually associated with MIT by quite a famous professor called Herbert Dreyfus. And I thought at this stage that going to seminary, I better start studying some philosophy, but I only had a background in physics. And I thought this would be a good bridging book, because the title of the book was What Computers Still Can't Do, a Critique of Artificial Reason. And I was enthralled by this book as it was a very careful philosophical study of why the way the human mind works is actually nothing like the way that a computer works. And this got me interested in the whole topic of the brain and neuroscience. And every now and again, this has cropped up again in philosophy and theology I've studied over the last few years. Most recently in a book that's gone well outside its original field, The Divided Brain and the Making of the Western World. The Master and His Emissary, The Divided Brain and the Making of the Western World. So the study of the brain teaches us something, but it's very hard to avoid making philosophical mistakes in applying neuroscience too quickly to issues of human and divine action. So I was very grateful to have Professor Holodny to speak with us as he actually studies the brain and is one of the best qualified people to do so. He's got a BA in physics from Columbia. He's MD from New Jersey Medical School. He's currently Professor of Radiology at Cornell, Chief of Neuroradiology at MSKCC, so you'll see the full name down on your timetable, Head of Functional MRI, also there, and founding President of the American Society of Functional Neuroradiology. He is an honorary doctorate from the Russian Academy of Science and an honorary member of the Minsk Theological Academy. So would you please welcome Professor Andrei Holodny.
Well, first of all, thank you very much for inviting me. I'm absolutely enthralled to be here. And I think anybody who's a scientist in the room understands that the hardest thing to do is to speak to non-scientists about scientific areas. So I'll give my best shot about it, but if somebody doesn't understand something, you're confused about something, I'm being incoherent, I start rambling about equations or something, just raise your hand and I'm completely okay with being interrupted. So here goes. You know, it's a little bit impolite maybe, but I'm going to tell you a little bit about what I do so that you understand where I'm coming from and you know, why I'm interested in this field. So I'm from Memorial Sloan Kettering, which is a cancer institute, and I study the brain, so hence I study brain tumors. Now with brain tumors, the most important thing, the more of the brain tumor you cut out, the better the patient does. The problem is that the brain is not the liver. You can cut out 90% of the liver and the person still works fine. You can cut out one kidney, the person still does great. But the brain is not like that. You can't cut out certain parts of the brain and have the person function afterwards. So what we do is we do functional magnetic resonance imaging to figure out where all these different areas are in the brain. And then we map them out in 3 dimensions, for example, here. Right, can people see the arrow? Right, so there's our brain tumor right here. And here I'm looking at simple things such as motor function. People come in, oops, sorry about that, and tap their fingers. And I can tell the neurosurgeon the exact relationship between the tumor here and, let's say, the area where the finger tapping is, or right here, right? This is another patient. That's our brain tumor. This is where the hand motor area is. Now, myself, I'm interested in much more interesting and complicated things that the brain does instead of just simple finger tapping. Higher cognitive function, ethics, language, things like that get very, very interesting and very, very exciting. And so that's kind of where I come from. Some more things that we do. So this is kind of where an open brain. What we do is I can, show this in 3 dimensions in real space. And, we can see where the tumor is. This is where the motor cortex is and things like that. This is kind of not all that important, but just kind of to show what we can do here and things like that. These are the images that we give to the neurosurgeon. He can operate much more safely, avoid certain areas, take out other areas of the brain. So this is the kind of the stuff that we do. And and this isn't a shameless plug for your book, but basically to understand what I do is, we take a person here, and then I make a math model of it, which is this MR scan, which is basically a bunch of numbers in some kind of order that I can look at, or a neurosurgeon can look at, and make some kind of assumptions that actually help this patient in terms of his or her health care. So the important thing here is that you can never have a model that's exactly as good as what you're looking at. All right, this is basically axiomatic. There's this joke that this one comedian stands up and he says, I have a map at home of the United States. It's 1 foot equals 1 foot, right? So you can't have that, obviously. So this is kind of the stuff that I do. Now, I'll start off with a quote from a 18th century French physicist. His name is Laplace, and this is known as either Laplace's Demon or Laplace's conjunction. And this is, I think, the philosophical basis for a lot of the arguments that the preceding speaker argued against. So let's just read it together. And Laplace says very famously, we may regard the present state of the universe as the effect of its past and the cause of its future. An intellect, or the demon, which he talks about, which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were so vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atoms. As such, for such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Now, this is a very bold statement by Laplace, but which many philosophers of science agree with to this day. Now, I have a problem with this. I just don't believe that it's true. But I have to, as a hard scientist myself, I have to justify my beliefs and thoughts on some kind of rationality or some kind of science. I can't just say, well, I think you're wrong, and that's it. That's kind of not how science works. Now, to me, there's a very interesting thinker. His name is Stephen Jay Gould, and he came up with this concept called NOMA, or non-overlapping magisteria, right? Science is over here, and that's all okay, and then religion is kind of over here, and they kind of don't mix and match. They believe, they're separate magisteria, and this is perhaps, the kindest thing that very famous philosophers of science have said about religion in a long time. And I still don't believe it. I mean, for me, there's something fundamentally wrong with my job being here, and then I believe in God, and it's over here, and the two kind of don't mix. I have a problem with that. So a lot of what I think about is how to kind of meld these together, and is it possible to meld these together at all? So this is kind of my attack, is to bring these two together, which are fundamentally unsatisfying to me as it stands. Now, here's an outline of what I'll talk about. One is I'll demonstrate that the brain is indeterministic. Wow. If it works, then it's very good. Then I'll talk about spontaneous neuronal activity. All right, spontaneous neuronal activity, another very big thing. And then I'll talk about some philosophical and theological consequences thereof, and then how they relate to the theme of the present conference, science and personal action. And away we go. So the first thing to understand is that neuronal activity is nonlinear. Fundamentally so. Linear means is that I do something and it's proportional to the outcome, right? I don't know, I put in $100 in the bank, and if there's a 10% return rate, it's $110. I put in $1,000, it's $1,100. These are linear understanding. Nonlinear is the following: how neurons work, right? At a synaptic junction, so what happens is neurons talk to each other by synapses. So there's a body called there's a body of the neuron. It has this long tail, and at the end it has this thing and touches onto the other neuron. And this is what a picture is over here. So basically what happens is it releases, giving away the show here. So it releases certain neurotransmitters. They go across, and they either can or they cannot set off the next neuron. Okay, it's either, so it turns into something that is a gradient to something that is base 2. Base 2 means yes or no, 1 or 0, right? Either one neuron sets off the other one or it doesn't. There's no gradations here. And what happens if you get a whole bunch of neurons together, right? All of these neurons are coming on together to to influence this one. They sum these up. There are excitatory potentials and inhibitory potentials. They all kind of add up together, and the system decides whether it gets set off or no. So there's many, many different inputs, and only one type of answer: yes or no. Does the next neuron fire? Does it not fire? And obviously, you get into complicated things, and they start looking like this. And it gets very, very, very complicated. Now, I'd like to show this graph, and this is, if people have, if you have 1 point for the lecture, this is my point. All right. So and this is a graph of any type of events, right? So this will be, some kind of events here, and this will be some kind of time, right? And this is a base 2 system. Something happens here, and something doesn't happen here. You can look at something like, I don't know, will I have a car accident going home? Right? So, and I could put on all these different factors. Well, is it raining? How much have I had to drink? Do I have a headache? Or kids yelling in my car? All these things will, what other drivers are doing and whatever, right? So if I cross this threshold, I will have a car accident. And if I don't cross this threshold, then I will not have a car accident, right? So a bunch of different things coming together to make a base 2 decision. Everybody okay? Any questions? So, and you can look at this for anything. Will the stock market go up? Will it go down? Will, somebody get pregnant? Will, I don't know, will I get married to this woman? Any amount of complicated things coming down to a base 2 decision. So what we have here is 2 different graphs, right? The red graph, it kind of ends below here, and we do not get the next event. All right, so in our neuronal system, all these things come together towards the neuron, and there's not enough juice to set the next neuron off. In the green graph, there is enough juice to set the next neuron off. Okay, everybody's okay with that? Now, so where indeterminism comes into play is if I can't measure something to the accuracy where I can differentiate between these 2 paths, then the system becomes indeterministic.
Would you say that again?
Sure. If the way I'll do some kind of measurement on some physical system, right? If my measurements aren't accurate enough to differentiate between these 2 paths, the system becomes indeterministic. I can't tell the difference between them. Okay, this is a fundamental point here. Everybody okay with that?
Not particularly.
Okay, all righty, okay. So, all righty, let's...
The point you're making is that we can't tell the future, so...
No. Let's get away from philosophy. Very simple physical system here, right? If I can't measure things to a certain accuracy, right, then let's say I'm a pool player, okay? Pool is, the classic Newtonian physical system, right? If I can't see that well, right, I can't aim the pool cue well enough, all right? If, in pure Newtonian physical things, I can, determine exactly if I hit the ball at this angle, if, the ball will go that way or will spin this way, right? If my hands are shaking, right, my angle is, 32 degrees plus or minus 5%. With that, I don't know if the pool will go into the cue. Or let's give another example. That is
the same thing as saying nobody knows.
That is absolutely correct.
What it's objecting to is the idea it is indeterminate versus it is indeterminate relative to my knowledge.
Guys, I'm not making philosophical points here, all right? All I'm doing is talking about the physics, all right? Everything I said is true. And everybody will agree with it, all right? From the worst atheist to the best saint, all right? This has nothing to do with philosophy yet. We're not up to that yet, okay? I want to understand the system, right? Or here, let me give you an example, right? Why is it so hard to shoot down a missile? All right? If you look at simple things, any high school physics student can solve those equations, right? If you throw in a little more complicated things, Coriolis forces, the curvature of the Earth, it's any, person who's taken sophomore level physics can solve these equations. So why is it so hard, right? The answer is the following. Well, we'll say, well, the missile is flying at 500 miles an hour, the wind is blowing 20 miles an hour this way, and your anti-missile is whatever. The problem is it's not flying at 500 miles an hour. It's flying at 502.36942 miles an hour, and then it hits an air pocket and it's going at 498 miles an hour, and then this is the problem, right? The problem is the measurement of the missile, right? Just like how fast is the wind blowing, right? Well, okay, wind's blowing 5 miles an hour. Well, no, it's not. It's blowing -2 miles an hour, and then it's blowing 12 miles an hour. And how can I test it, right? I'll have to test it by putting a sensor in every little space, and I can't do that, right? That's why shooting down missile technology, it senses, there's a sensor on it, it senses how close it gets and things like that, right? But this is, everybody understand right now? Again, this is pure simple physics, no philosophy yet, okay? My critics in the front row here. Okay, so this is, now, if we get to problems of measurement, right? In quantum, there's a Heisenberg uncertainty principle, which we all know about. And there's set theory of Laplace's conjecture, why it's false, and I could talk about that later if anybody's interested. Now, in biological systems, the question, is there a Heisenberg uncertainty principle in biology? That is unique to biology and more than in physical systems. Because the problems with quantum mechanics is people say, well, all the quantitative effects wash out in a macro system, right? I don't have any quantum effects on me right now, right? They all wash out. Now, so is there a fundamental limit to what we can measure in a biological system? And question number 2, does the act of measuring affect the system being measured? Right, this was originally Heisenberg's uncertainty principle, but that's kind of frowned upon right now. But does this still exist in biological systems? Now, here's a simple example, right? How tall is Michael Jordan? Right, so we can go to Google, Michael Jordan, Wikipedia says Michael Jordan born Sunday, 6'6", right? But that's not true. And I'll tell you exactly why. Because people's height changes as much as an inch during the course of the day. There are reasons for that, right? What happens is that the discs in my back are filled with water. When I walk around during the day, they get compressed, they get smaller. And it's especially true in children, right? And then when I lay in a horizontal position, they get filled up with water again, plus or minus 1 inch, right? Now you might say, well, who cares, right? Now, let's say I want to calculate, it's down to the, last 5 seconds. Michael Jordan has the ball. He's going up against, I don't know, some other basketball player, or Larry Bird or whoever. And I want to calculate if Larry's going to block Michael's shot, right? Now, if Larry Bird is, if he's 100% going to block it, well, then that's easy, right? But the trick becomes right at that border where the difference becomes very, very small. Okay, let me just back up a second, back to here, right? So back to this slide right here, right? Now, let's say in terms of neurological questions, right? If you ask me, well, what is 2 + 2? I'll always say 4, right? Or let's say the doctor hits me in my patellar tendon, my knee is always going to bounce forward, right? But let's say you ask me, well, who's right, Plato or Aristotle, right? What's the best answer to E4 in chess, right? This becomes a much, much more complicated question, right? I have some 50 billion neurons left in my brain. They each have 1,000 connections. They shoot off about 1,000 impulses per minute. So that's 50 quadrillion operations in a minute. right? And this is me just thinking for a minute. If we think about the Plato versus Aristotle question, that's, a lot of really, really smart people thinking for a really, really long time. What happens here is that the difference between the green line and the red line becomes very, very, very small. Okay? So getting back to Michael Jordan, right? So we see that, Michael Jordan's 6'6" plus or minus, 1.5 inches. Okay? Now, the human body and the human brain changes over time. Some things are simple, right? Child goes to an adolescent, to a mature brain, an older adult. There's that famous, soliloquy from the Shawshank Redemption where the old prisoner, says, of course I committed that crime, and I was, that was some stupid kid, who's like no longer around, but this old man is all that's left. But it's the same person, right? And he's changed cognitively, he's changed ethically, he's changed morally, but he's still the same person who committed that crime. By the way, there's very interesting stuff in neuro-law in terms of this, right? The vast majority of violent crimes are committed by males between 15 and 30 years old. The vast, vast majority. Is it really that person who's committing that crime? If he's, once he's 40 years old, does he change? It has to do with, sentencing laws and things like this. Very interesting work in terms of that. So, first of all, the brain or the human mind changes over time. Now, more than that, our brain is changing physically all of the time. Every time I have a memory is a physical change in my mind. I met a bunch of new people. They're somewhere stored in my memory. My brain is changed. And I'd like to, set a little bit on this, beating heart physically changes our brain. Now, what happens, how the brain works is, right, when the heart pumps blood, right, there's, let's say, an ejection fraction of the left ventricle is about 150 cc's. Approximately 10% of that goes into the brain. And the brain is about 1,300 cc's. So over the course of the time, what happens is the brain, you can see the brain pulsating, right? You can see that during neurosurgery, or we've all seen horror movies as kids where the brain is pulsating. And it actually does. So what does that mean in terms of our problem? Number one, the brain is not a single organ. The brain physically changes by plus or minus 4%, 1% plus or minus for every breath, 1% plus or minus for every breath that I take, right? What happens when I take a deep breath, I suck out all the venous blood from my head, and the cerebrospinal fluid, which bathes the brain, if you will, changes, and the geometry of the brain itself changes with every heartbeat to a significant amount, and with every breath that I take. So, there's an old philosophical question, if I ask myself a philosophical, a question 100 times over, and let's say we eliminate memory from this, will I always answer it the same way, or will I answer it, 63% of the time one way, and 37% of the time the other way, right? This question's bounced around. Now, I've just answered it. Right? If you answer, if you ask me 2 plus 2, it doesn't matter what, systolic, whether my heart's beating or it's not or whatever, right? I'll always answer 2. But difficult questions, where I'm right near that threshold, the answer can change because my brain is physically different. Right? Not only is it physically different, it's physically different in a nonlinear way. Right? These are waves of blood flow that are changing how my brain physically works. Right? If you look at the arteries, and this is kind of the stuff I do a little bit, is you can actually see how the brain moves, see how the cerebrospinal fluid moves, see how the blood in the arteries or in the veins change with every heartbeat. Right? So, therefore, if we ask, again, a complicated question that's near that threshold, the answer can be different based on which part of systole I'm asking the question in. Okay, again, these are not 0.00001 changes. This is a 4% change at rest. At rest. All right, when I get excited, even more things, more interesting things happen, right? So, I had a friend of mine, he was the first one to demonstrate by MR that how the brain moves and pushes the cerebral spinal fluid around. He came up with this phrase, the brain is just a pump, which is, I thought was cute, and I put this into it. But what's interesting is that, maybe the heart does control the mind, which I think sort of just demonstrated just a little bit. And this, can be a cute, title to some article in the Sunday Times or something like that. I don't know. Anyway, but it gets more complicated than that. Gets more complicated than that. And this is, the gentleman over there mentioned feedback loops, right? That happen in biology all the time, that happen in, biochemistry or whatnot. This also happens in this effect, right? So if this is a cartoon, each one of these little stars is a neuron, and this is a vascular tree. This is, blood vessels that go to these neurons. So what happens, let's say these neurons, they become yellow, they start activating. So what happens when I start moving my fingers in my hand? More blood goes to the area of the brain that is controlling that area, right? So, and this is the basis for bold fMRI. People have, I'm sure, have heard of fMRI. It's, everywhere, cigarette commercials or whatever, functional MRI. So this is kind of how it works. And, if you want to, figure out, how simple the things I do are, or to be, sharp in front of your friends at some cocktail party. This is kind of how fMRI works. So there's an increase in, see, these neurons start firing. There's an increase in the blood flow there. Everybody knows that blood has hemoglobin in it, right? Everybody knows that hemoglobin has a little iron atom in it. Everybody knows that iron is a little magnet, right? So these magnets that flow through the magnetic field in my magnetic resonance imaging scanner is what causes the bold fMRI effect, and how I can use this to see all these things that I do. I beg forgiveness from any physicists. Anyway, so, and this is, kind of what I can see. So what happens is, and this is actually very interesting, because what happens when there's an increase in neuronal activity, there's an increase in the oxygen consumption, which means that the neurons, they're working harder, so they're sucking more oxygen out of the blood flow. But what happens, paradoxically, is that there's a much greater increase in the blood flow than is necessary there, right? The point to our discussion is that the change in the blood flow even changes the geometry of what is going on, right? If, let's say, you have two neurons together, and you got a big artery sitting right here, if the artery is beating, it's changing the geometry between these two neurons, right? This is basically the cause for, trigeminal neuralgia and things like that. And people actually have surgery to go in there, remove that blood vessel from pushing on these different nerves. So this is a feedback loop, which not only works in terms of, what I just described, but only adds extra layers of complexity in terms of this, right? Also, and if we think about how the heart beats, right? It's very few people have an extremely regular heartbeat. Nobody has a regular heartbeat when it comes to doing exercise or things like this. I get worried or sad or whatever. My heartbeat changes from that, right? This is a relationship between what's happening in my brain and what's happening in my heart. So to say, 5 minutes from now, where in the systolic heartbeat will I be is basically impossible. Therefore, if you ask me, what will my answer be to a question you're going to ask me in 5 minutes, where I'm right on that borderline, I won't be able to say which way my brain will answer. And hence an indeterministic system. Okay? Now, a few more examples of some, basically non-trivial examples of how difficult measurements are in biology. Now, physicists can calculate, let's say, the mass of an electron at rest to 50, decimal points, and they're all very good at that. In biology and neurobiology, we're nowhere near that. Nowhere near that. Let's say neuropathologists, right, of brain tumors. There's an approximately 30 to 40% disagreement in terms of what the pathology of this brain tumor is by experts in the field And this is after 150 years of studying this field. All right? It's not a 1 or 2% difference, some beginner guy versus some expert. These are, pathologists from Memorial Sloan Kettering, Mass General, MD Anderson, and there is this huge difference of opinion. This is how measurements work in biology, all right? Measurements of dimensions of a brain tumor on MRI, what I do every day, right? How big is the brain tumor? So there are different criteria to discern whether some brain tumor has gotten bigger or not. And that you need a 25% change. 25%. That's a huge difference, right? But I can't get better than that. And MRI has been around for 30, 40 years. We do millions of scans a year, and we're still not better than that, right? So biological measurements are notoriously messy. And even in terms of things like, people do single neuron measurements of, light. They dissect some cat, and then they take out the neuron from the retina, and they shoot, a certain number of photons at it. And these differences are 30 to 40% in extremely well-controlled examples. 30 to 40% differences. So this is just to show that. And here is more examples in terms of biology where the act of measuring causes a change in what is measured. All right, my act of measuring causes this change. The white coat phenomenon, probably the simplest example, you go to the doctor's office, he's got a white coat on, he's got the stethoscope, and you suddenly start nerving that you got clogged arteries or whatever. You're sitting there, you get all nervous, your heartbeat goes up, right? So the fact that the doctor walked into the room drove your blood pressure up, and he says, calm down, everything's going to be okay, this and that, lie down, have a glass of water. He measures it, and then it kind of becomes normal. So this is kind of a trivial example. Now, a non-trivial example is CT scanning or mammography. All right, these are radiological examinations that we do. What we do is we shoot X-rays through people, right? There's some kind of X-ray source here. There's some kind of X-ray detector here. They shoot these X-rays through me, and the detector detects it, and that becomes mammography or CT scanning or whatever. Now, the problem with that is that shooting these X-rays through me increases the rate of my mutations, right? So the problem, let's say, that we face every day is, you had some kid who had, leukemia, retinoblastoma 20 years ago, and he comes in for a CT scan every, 3 or 6 months. Well, I'm just dumping a whole lot of radiation into this kid, which raises the chances of 1, recurrence, or 2, getting secondary cancers, right? In women, one of the big problems with mammography is that mammography itself increases the rate of cancer, right? So that doing this test actually affects the result. All right, and there are many, many things that we can do, or limits to how much energy we can pump into a living system. Right, MR is limited by how much heat the scan can dump into a person, and then there's all different ways of calculating it and things like that. And that's why I don't have such great resolution of my MR scanners, because there are limits to what I can do, even a benign technology such as magnetic resonance imaging. Right. Biopsies are interventional procedures, right? We all know biopsy. The doctor comes in, sticks a needle somewhere, finds out what that is, benign, malignant, inflammatory, what have you. Right, first of all, it can hurt the patient, right? Brain biopsies, the doctor goes in there, does a biopsy, you have a brain bleed afterwards, right? Doing the test affected the test subject. Right? Another interesting thing about biopsies is that you're measuring what's no longer left in the body. Right? By definition, what you're measuring is no longer on the body. It's on the slide of the pathologist. Right? So it's only a reflection of what is left. Right? Sometimes they resect the whole tumor, and there's nothing left. So there's a malignant tumor over here, nothing left in the person. Okay, so it appears that there are fundamental limits to measurements in biology and neuroscience, which are much, much greater than any kind of fundamental limits in, let's say, the physical sciences or chemistry, right? I can't pump, 100 GeV electrons into people and see what happens. You just can't do that, right? These fundamental limits are signal and noise. Noise will never be zero in a biological system. Never. Right? Let's say I want to measure what's going on in my head, right? What's going on in my brain, right? I can do two things. One is shoot some kind of energy in me and then see what comes back at me, all right? And then the other thing is try to look at intrinsic brain activity and try to measure that. So the first two examples would be MR. I'd be shooting, MR waves into that, or CT. I'd be shooting, light particles into it. Versus, let's say, MEG. What MEG is they put sensors all over the head and then measure the little magnetic changes that happen in the brain, do the electrical changes, and then kind of have a map of this that comes out. The problem with that is that getting from the brain, you have to go through a thick skull, you have to go through the meninges, through the hair, through the skin, through this. All these things have, salts in them, have all these other things that degrade the signal. And there's no way around that. There's no way around it. You can't get to that without it, right? Now let's say, well, I don't know, let's put in an electrode. Well, okay, well, you just stuck a needle into somebody's brain, right? Now there are 50 billion, there was this project, this huge grant in Germany. It was a big fiasco. They, about a year ago they came out with it. They wanted in 10 years to figure out how the brain works. Impossible, right? Impossible. Why? Because let's just say that I'll put an electrode into every single neuron in the brain. I've figured out how to do that. All right, I figured out how to do that. I've got 50 billion needles sticking in this person's brain that's not going to affect him, all right? This is beyond science fiction, right? I'm still not going to know how the brain works, right? Because how the signal changes, how the signal moves down an axon changes, that we discovered a very simple mechanism, and there are many more complicated mechanisms, by whether there's a beating blood vessel next to it. Right? So if I take a measurement of this neuron over here, I won't be able to predict what it is a little further down. And that's if I have 50 billion needles sticking in somebody's brain and he doesn't even notice that this is going on. All righty? So biological systems change over time. Hence, a measurement at time A will actually be different at a time B when this measurement is used to make a prediction. Okay, how do things work? I'll measure this basketball and it weighs, 1 pound or whatever, and then I'll measure, how my hand moves, and then I'll figure out whether it goes into the bucket or no, right? But if I measure this basketball at time A, and then by the time I'm ready to shoot it, it changed its weight or it changed its configuration, I'm not going to get the right answer. And this is what happens with the human brain. The target is changing always, right? An example of this is, weighing the boxer at a weigh-in versus the weight at the start of the fight, right? By the weigh-in, they try to make weight. They're all very thin, and then they go eat these huge steaks to get their strength back up. Okay, so fighters are often 10 pounds more at the start of the fight versus what they were at the weigh-in. And this is what's happening in our biological systems. Biomarkers, okay? Biomarkers, we hear a lot of this word, knocked around, especially, when you try to apply to grants at the National Institute of Health. And, this is kind of what I do. I have, math models of the brain versus the real brain, right? So biomarker is a substitute from what we really want to measure but can't, okay? The tumor grade is a biomarker for patient survival. Right? Honestly, I couldn't care less what the tumor grade is. I want to find out what's going to happen to the patient in 6 months, in 12 months. There's no way that I can figure that out. So instead of that, I have something that kind of approximates and gives me kind of an idea of what's going to happen in the future. And this is what biomarkers are. And there's, perfusion of brain tumors, this and that. There's, millions of different kinds of biomarkers that try to help me to predict it. But again, it is a substitute for something that I really want to know, right? People will, come in with a tumor and they'll say, well, doc, how much do I have left to live? Answer is, I don't know. I don't know. Right? I can give you a percentage. I can say, well, chances are 43% you'll be alive in 6 months, and whatever, you'll be alive in 12 months, and things like that. But Weird things happen in medicine, and they happen in medicine a lot. And this goes to, you know, the gentleman that talked to me before, Hume's arguments, right? Hume's arguments. Hume will say, well, you know, in terms of, let's say, I've never seen, you know, the sun rise from the west, right? And therefore, you know, it never happens, and therefore miracles don't happen. Well, you know, miracles, if you will, or weird things, if I'm an atheist, happen in medicine all the time. People with glioblastomas, the most deadly cancer there is, alive 20 years from now. Does it happen? Sure it happens. It happens all the time. Horrible cancers just, and it's not there anymore. Why does that happen? You know, to me, Hume's argument is nonsense, because I see these things all the time. And if we look at nature carefully, right, not having our own, you know, I decided that the world works like this and therefore it works like this type of argument. I mean, I could show you things that just have no reason, no rhyme or reason for happening. Happens in medicine all the time. Maybe in Memorial Sloan Kettering more often than at other places because we get the real weird cancer cases. But this type of stuff happens all the time. Now, why it happens, well, that's a discussion for theologians. But extremely unexpected things, absolutely all the time. So, two, a lot of measurements, and this is something I haven't raised before, are purely subjective. Pain. There's no objective measurement for it. It is purely subjective by definition. Now I can do some functional MRI studies to see how, you know, what thalamic nuclei light up when I'm, you know, torturing some graduate student by sticking needles in his fingers. Sure, I can do that, right? Or I can, you know, give them aspirin and see what happens, or, you know, have them do Tai Chi or something before. I can measure all these things, but it's not a measure of pain. This is a big problem, right? Let's say, I don't know, you want to see if some aspirin works better than Advil, right? How do you do it? Right? What people do is, you know, they'll have a scale of 0 to 10, and you'll mark it somewhere. All right, yeah, my pain's about a 6. Right? That's as good as we get in biology. Right? This is the best that we will ever get. We will ever get in biology. Right? So, and the last question is ethics. Right? Now, hopefully, we'll never ever go back to, you know, torturing people to find out some medical things or whatnot. But there are certain tests that just can't be done. Can't be done. I'll give you an example. So our functional MR society, right? The images that I saw where you can, you know, see where, let's say, the language area is in the brain versus where the tumor is in the brain, right? So the way to, we had a great technique. You know, I was younger, bright-eyed, bushy-tailed. I want to show that this works, prove it in scientific manner. So what you have to do is you have to do a double-blinded prospective study, right? What's the problem with this? Nobody will sign up for it. Right? Let's say I come to a patient, right? Patient has a brain tumor, and I'll say, well, we're running this study, and in one way, we'll do this test, and we'll be able to see where the language area is, where the tumor is, and the other one, well, we'll kind of just guess. And, you know, and it's random which one you get into. There's not a single patient that would sign up, and we tried it. It doesn't work. They said, no, doc, I want that test. Right? And the same with the neurosurgeon, right? No, not a single neurosurgeon will sign up for that. Why? Because it makes his surgery better. Or, I don't know, microscopes in the operating room. There's not a single study that show that they work. Because it's obvious that it works, right? But I can't prove it in terms of science. Right? And some things are just unethical to do, right? Doing a study like that would border on the non-ethical, because I'm denying something to patients that's clearly better to move forward some kind of scientific idea. Okay, moving on to something else, and that is spontaneous brain activity, all right? And this is a very interesting topic, and I'd like to show this to you from this YouTube video, just kind of what happens, right? So these are, you know, they basically, what you can do is you can put neurons into a petri dish, and they'll start shooting off their signals to their neighbors. And this happens in the developing person. Oh, it goes on to the next one. Oh, let me get rid of that. Oops. And And this is, something that's very, very interesting, right? Because neuronal activity appears, there's no neuronal activity, and then there's, for some reason, some kind of thinking going on. And it is a self-organizing system. A self-organizing system where greater organization comes from an area of lesser organization. And this is a very, very interesting and very controversial topic in a lot of things. Chaos theory, self-organizing chaotic things in terms of math. Or let's say, how did the DNA organize first of all? Was it RNA first? These are self-organizing systems that for some reason can take a more basic structure and form more complicated structures. Now, this does not go against the second law of thermodynamics, because if you add everything together, the order in the more basic system was still greater than the order in the more complicated system. But these things occur, and I just showed you a movie of how this stuff occurs. And I think this has very interesting philosophical implications. Okay, another interesting thing where I actually know something about is resting state fMRI. So how does regular fMRI work? And I'm sorry I promise no equations, but I'll show pictures. So if this is actually me in the scanner, and I'm wagging my tongue, and this is an area of the tongue that's active. So if, basically how it works is the following. I will scan myself every 2 seconds, right? So I scan my entire brain. Every 2 seconds I acquire this data. And so this is time, and this is the signal intensity in, let's say, this voxel right over here, right? So as you can see, even by the naked eye, so this is the blue line is the signal intensity in that voxel over time. And the red line is here I'm holding my tongue still, here I'm wagging my tongue, here I'm holding my tongue still, here I'm wagging my tongue, etc. Right? So what happens in this area of the brain through the mechanism I just described earlier, you can see even with the naked eye that there's a peak in the signal that matches when I'm wagging my tail. Okay, this means that there's more blood flow there, implies that there's neuronal activity, implies that this activity has to do with my tongue wagging. And therefore, on our MRI scanner, this gets a yellow dot, right? And there's these many different things, and people get PhD theses on what kind of math modeling you have to do about that, and they argue about that all the time. But basically, you can see here, even with the naked eye, that there's some kind of matching going on here, right? As opposed to a different area of the brain right here, that this is kind of random noise versus the paradigm, the tongue tapping paradigm. Okay, so this is kind of noise, and this is kind of signal that matches this. This is why this area gets the yellow dot and is actually going, I can define that function is going on there. Now, Bharat Biswal is a very smart guy, and he looked at the physiological noise, in quotation marks, in the brain. And it turns out that this noise actually has a lot of structure. All right? So what does it mean is, the brain has a lot of activity during resting state when it's doing nothing. In fact, the vast majority of the activity of the brain has to do when it's at rest, when I'm sitting there not thinking about anything. The changes that happen when I start, moving my, fingers in my hand or thinking about ethical questions or doing some kind of language paradigm, those are changes of 1% to 2% in terms of the energy consumption. The vast majority is just how the brain just sits there and kind of does nothing. So in this, we know that from PET scan. PET scanners are very hot. You look at this little kid that we're torturing with over here. I'm not torturing. Putting electrodes on this kid. This kid's asleep, and yet there's a heck of a lot of stuff going on in that kid's brain, right? Or MEG, this is kind of like the same thing. So what Bharat Biswal figured out is that in resting state MR, just put the patient in the scanner and have the patient do absolutely nothing. Close their eyes, not think of anything, get ready for sleep. So what he figured out is that the noise, let's say this is the area of the right hand, motor area of the right hand. This is the motor area of the left hand. And this is what's known as the supplementary motor area. And all of these things compromise basically the motor structure of the hand. All right? All of these things are involved in moving the hand. And if you look at the noise, if you will, in the right hand versus the noise in the left hand, these signals match almost exactly. Stunning discovery. Stunning. I think Bharat should win the Nobel Prize for this. All right? And there's no rhyme or reason for this, why this happens. I would have never guessed this in a million years, but he was smart enough to figure this stuff out. And this is the basis for resting state fMRI. All right, so this is just some stuff from our group. And again, you can see that one hand, matches exactly with the other side. And you can see the supplementary motor area and whatnot. And what you can dig out, now let's say paradigm-driven fMRI, if I do it, let's say just moving the fingers in my hand, I can see only the activity caused by the fingers in my hand. From the resting state data, I can see a myriad of different functions. Right? One is the default mode network, and I'll come back to that a little bit, right? And this is all from one fMRI run, right? Somatosensory cortex, auditive system, visual cortices, what have you, right? I would like to talk a little bit about the default mode network. The default mode network is the brightest when the person is laying there and not doing anything. All right? This is what the brain is kind of thinking about, if you will, at rest. There's a lot of wonderful work about this and a lot of kind of speculative at work. I don't know about anybody else, but I get my best thinking done is just when I'm ready to go to sleep. I always have these great ideas come up. I have to wake up and write them down or something before I forget them. I try to tell my wife this like it's Saturday afternoon and it's raining out and I'm going to be thinking about great things while I'm laying on the couch with my eyes closed, and she doesn't buy that. So anyway, but maybe Descartes did that, right? When he would wake up and lay in bed until lunchtime and think about great things. Anyway, so this is kind of the thoughts of where the default mode network runs. What happens is if I do an experiment and I, let's say, start moving my fingers in my hand, or I do some kind of language paradigm, the default mode network starts to deregulate, gets lower. All right, and if anybody's interested in this, there's a great guy named Regal from the Washington University of St. Louis. He does a lot of really wonderful work on this and what it kind of means in terms of philosophy. So what this shows is that the brain, even when I'm at rest, is thinking, and is thinking a lot. All right, the brain is actually extremely, extremely active, even when I'm not thinking about anything. Oh, you want you to shut up? Okay, all right. I'm getting close to the end. Sorry about this. So, and this kind of cause is unknown to Aristotle, I think. And now here I need people's help in the room. Feel free to criticize me because I can be absolutely wrong. But it seems that if we do this experiment, the brain is causing itself. The brain is thinking about itself, right? If we look at this, does not fit into the Pavlovian schemes, right? Pavlov thought, show somebody a steak, acts on the brain, and the brain causes our dog to salivate. That's how Pavlov's ideas, right? Everything that we do is some kind of reaction to some kind of outside stimuli. The brain kind of thinks about it, and we get some kind of input. It turns out, well, no. The brain can be a cause of itself. The brain can cause these things by itself without any kind of external stimuli. All right, so I'd like to acknowledge all the members in my lab here, without whom I would have done none of this work, and thank you very much.